Okay, so in this video we're going to be talking about how to write decay equations for different types of radioactive decay, and more generally how to do nuclear reaction equations. In the last video we talked about the three main types of radioactive decay. And remember, you have radioactive decay when you have an atom that has an unstable nucleus, meaning there's an imbalance between the strong nuclear force holding the nucleus in and the electric force between the protons inside the nucleus that's a repulsive force. Okay, and the three main types of radioactive decay are alpha, beta, and gamma decay. We talked about the properties of those particles in the last video. Remember, there's actually two types of beta particles. A beta minus particle is just an electron. Of course, it was named before we knew that. And a beta plus particle is what's called a positron, which is a positive electron. Okay, which is basically the exact same thing as an electron, just with a positive charge. Okay, so we kind of left off about here. Just some general notes about these types of radioactive decay. Alpha decay, you typically have alpha decay when you have a very heavy nucleus. And so everything past iron on the periodic table is inherently unstable. And the reason that is because at some point the nucleus gets so big, there's so many nucleons inside the nucleus that no matter what happens, the nucleus cannot be held together. Okay, and so that's why every element past lead on the I said iron before, but I meant lead. Every element past lead on the periodic table is unstable. That means radioactive. Okay, so I believe lead is atomic number 82. So any element with an atomic number higher than 82 would be inherently radioactive, and typically something that heavy undergoes alpha decay. Now, you can have radioactive elements below lead that are radioactive, but those typically experience either beta minus decay or beta plus decay. Okay, and so here is just a graph, and this is called the band of stability, and basically each of these little dots is showing you just different types of nuclei, either stable or unstable. These black lines, let me see if I can zoom in here. Each of these black squares here represents a stable nuclide, and then the other colored squares represents different types of radioactive decay, and it's labeled here on the right, beta plus, beta minus, alpha. Notice you typically have alpha at the higher end of the spectrum for the really heavy unstable nuclei, and then you kind of have a mixture of beta minus and beta plus down here. The graph you're looking at is you have the number of neutrons on the y-axis and the number of protons, the atomic number, on the x-axis. Okay, and so elements that undergo beta minus decay, you can see, are on the top of this graph, meaning that that type of decay tends to happen when you have too many neutrons inside the nucleus, and that throws off the whole stability thing. Whereas beta plus decay, you can see down here, tends to happen when you don't have enough neutrons. Okay, so there's lots of different types of radioactive decay. I don't want to get into how would you predict which one is which, just to show you the general trends. And this slide right here is basically the same information. The valley of stability, this graph calls it. Okay, with the alpha, the radionuclei that undergo alpha decay tending to be at the high end, and then at the lower end you have either beta minus or beta plus, and you'll never have a question where you need to predict which one is which. I'm just sharing this information just so you know it. Okay, so we have talked about this before. What is it that causes nuclei to be unstable? And so I'm just going to make the slide bigger. Pause it here if you need to take notes. What it says is substances which do not have a balance between the strong nuclear force and electrical forces within their nuclei are unstable and leak is in quotation marks, this energy out through radioactive decay. Okay, generally speaking, you can make a nucleus more stable by adding neutrons. At some point, however, the nucleus becomes so full that not even adding more neutrons will make it more stable. The last stable atom is lead with an atomic number of 82. I said that before. Therefore, all radioactive substances emit radiation, either alpha, beta, or gamma, in some attempt to become more stable. Sometimes it works and sometimes it doesn't. So let me explain the first part of that. in some attempt to become more stable. It's one of the key laws of the universe, and I'm simplifying here, but one of the laws of this universe is everything that's in the higher energy state wants to go to a lower energy state. For example, if you drop a baseball, if you hold it above the ground and you let it go, it naturally wants to go from a higher energy state to a lower energy state. Okay, it wants to go from an excited state to a less excited state. And radioactive atoms are the same way. Okay, they are radioactive, they're unstable, and basically they want to become stable. And so they are going to emit some type of energy, some type of radiation particle, either an alpha particle, beta particle, or gamma particle, because they want to end up more stable. Now, the second sentence there, sometimes it works, sometimes it doesn't. Here's what I mean by that. Okay, so it is possible for something that is radioactive to emit one of those radiation particles and become something that is stable. However, it's also possible that something that is radioactive emits one of those types of radiation particles and then turns into something else that is also itself unstable, that is also itself radioactive. So what we're seeing here is at the top we have uranium-238. And uranium-238 naturally undergoes radioactive decay. It's an unstable atom, and it undergoes alpha decay, as a matter of fact, and it turns into thorium-234. Okay, now thorium-234 is also unstable, it's also radioactive, and it just so happens that thorium-234 undergoes beta minus decay and turns into, I believe that's palladium-234, which guess what is also unstable, that undergoes beta decay and turns into uranium-234, and so on and so forth. Okay, and so it's possible something radioactive is going to immediately decay after it emits its radiation into something that is stable. But it's also possible that you get like a decay chain like this. Okay, and if you follow the chain, what you see is at the very end of the chain, you finally end up with something that is stable. That is down here at the bottom, lead-206. Okay, so lead-206 is not radioactive, it is stable. But that means if you have a piece of rock that's 100% uranium-238, if you wait long enough, eventually all of the uranium-238 is going to be gone because it's going to have decayed, and at the very end, you're going to be left with lead-206. And the reason I bring this up, number one, is just to show you that something can decay into something stable or something unstable, and then you get this decay chain. And number two, this decay chain that we're looking at is used in what's called uranium lead dating, and it is commonly used to date rocks that are very, very, very old. Um, it's often said that the Earth is billions of years old, and one way that we know that is through this uranium lead dating. And so I'm not going to go into details now. You can easily look at videos about uranium lead dating on YouTube. But basically, in essence, is if you take a rock, when the Earth was formed, if it had just uranium-238 in it, we can now look at that rock today and measure how much lead versus uranium there is in that rock. And based off of that ratio, we can estimate how long ago that rock was formed, and therefore be able to approximate the age of the Earth. Okay, and so if you ever want to know how do we know how old the moon is, or how do we know how old the Earth is? One of the ways we know that is based off of this uranium lead dating. Okay, so I just thought I would share that with you. So there are some videos. I'll throw the links up to these videos here in a second. But mainly what I want to talk about today is, I'm going to skip past this for now. We're going to come back to ionization later. What I want to talk about is nuclear decay equations. Okay, and before we talk about that, let me just show you what these decays might look like using a simulation. Now, unfortunately, the website that does the simulation is no longer functional for us, and so rather than actually look at the simulation, we have to look at a video of the simulation. Okay, so here is what the video looks like. What we start off with is polonium-211. And polonium-211 is unstable, it's a radioactive atom. And what we're going to see is, in just a second, because it's unstable, it is going to undergo decay, and it's going to emit a particle. Okay, so let's turn the sound off, actually. And let's see that happen again. Boom. It happened already. Okay, now it happened so quickly you might have missed it, but we start with polonium-211, and we end up, a split second later, we end up with lead-207. Okay, so in other words, we started with one element, one atom, and we ended up with another. Okay, now you might have missed it because it happened so fast. Let me back it up and see if we can see it again. But right here, right when that unstable atom turned into lead-207, a particle came out. Now, what type of particle is this? This is an alpha particle. We can see the 2 protons and the 2 neutrons. Remember, an alpha particle is just a helium nucleus, 2 protons and 2 neutrons. And so this is a type of alpha decay. Okay, so what we just saw in that split instant was one single atom of polonium decaying into lead-207. And we want to be able to write this radioactive decay using what's called a decay equation. And the way we're going to do that, or the way we would do that for that example, is we would start with, what do we have at the beginning? We have polonium 211. Now, I don't happen to know the atomic number for polonium off the top of my head. On the next assignment, you're going to have a periodic table that you can use as a reference to completely fill this out. But I'm going to start with polonium, and I'm going to use an arrow to represent that polonium is turning into. Let's think, what did we end up with? What was our product? Okay, we ended up with lead, which is Pb207, and after the polonium turned into lead, it did that by ejecting a particle. Now, what type of particle was created? It was an alpha particle, which we learned in the last video is 4,2 helium. Okay, and so this right here is a nuclear reaction equation. This is the reaction equation for the radioactive decay that we just saw in the video. Okay, and so we write these equations to represent different types of nuclear processes. Now there's different types of nuclear reaction besides radioactive decay, and we'll see those in the next unit. Okay, but this is an example of a radioactive decay equation. On the left side, we have what we start with, our unstable atom, and on the right side, we end up with our product, what we call our daughter nuclei, and what type of radiation was emitted. Okay, so this is an example of alpha decay. I know it's alpha decay because there's an alpha particle being emitted. Okay, so that is an example of a nuclear reaction equation, specifically a nuclear decay equation. Okay, so pause it there if you need to add that to your notes. Okay, now I also want to show you a similar simulation for beta decay. And for this simulation, we have, let's see, hydrogen 3. And let me turn the sound off. Okay, so hydrogen 3 is unstable, it's radioactive, and in just a second we'll see it's going to decay, turn into a new type of atom, and in the process emit its radiation. Now, watch this. There. Okay, it happened in a split second. There. Okay, now notice the hydrogen 3 is now helium 3, but this time 2 particles came out. In the last video we talked about, I just briefly mentioned that in beta decay, you have a particle, an extra particle called a neutrino or an antineutrino. Okay, and so we'll talk about that here in just a second. But this is what beta decay would look like. Notice we started with hydrogen 3, we ended up with helium 3, and now 2 particles came out. One is the beta particle, and one is the neutrino. And so what I'm going to do now is I'm going to show you what the nuclear reaction equation would look like for this radioactive decay. So I started with hydrogen 3. I just happen to know the atomic number for hydrogen is 1, of course. Notice with radioactive decay, you always have only one thing on the left side, only one thing on the reactant side. Okay, that's not true for other types of nuclear reactions, but it is true for radioactive decay. My product that I ended up with after the decay happened was helium 3. I happen to know helium has an atomic number of 2. Okay, and now what came out was an electron and an antineutrino. Now, I just read a lot of new stuff on here, so let me explain. First of all, you might say, well, how did you know it was beta minus and not beta plus decay? Okay, so let me point something out to you. Something true for any type of nuclear reaction is if you look at the top numbers, the mass numbers, they have to be the same on both sides of the equation. So think of this arrow as an equal sign. Everything on the left is before the reaction happens. Everything on the right side is a product of that reaction, so after the reaction happens, and the mass numbers have to balance out on both sides of the equation. So for example, 3 plus, or sorry, 3 has to equal 3 plus 0 plus 0. Okay, now the same thing has to be true for the atomic numbers on the bottom. So if I have 1 on the left side of this equation, I know that 2 plus something has to equal 1, and so I can just figure out just by looking at that has to be a -1, and therefore it has to be beta minus decay. Now, anytime you have beta minus decay, you always get what's called an antineutrino. Now, an antineutrino, you don't need to know why. We'll talk about that in IB physics too. But an antineutrino is a particle that basically has no mass. It has no mass number. It has no atomic number. But you do need to include it for completeness. Now, the symbol for a neutrino looks something like this, kind of like a fancy looking V. A particle with a line over it is an antiparticle. Okay, so this right here is a symbol for an antineutrino. This would be a symbol for a normal neutrino. You have an antineutrino when you have beta minus decay, and you have a normal neutrino when you have beta plus decay. Now again, the reason for that, you don't need to know about that now. We'll talk about that in IB physics 2. Okay, so because this is beta minus decay, I've included my antineutrino in the equation. And because the numbers are 0, 0, that doesn't really change anything about my equations. Okay, so these are two examples of radioactive decay equations based off of the simulations we just saw. Now, before I end this video, I'm going to pause it here and write this down in your notes if you need to. Okay, I'm just going to do a few more examples. Here in just a second. You might want to add this to your notes before we move on. Okay, so pause it here if you need to. We're talking about writing nuclear reaction equations. The only type of equation we've seen so far is a radioactive decay equation. The other three we'll see in the next unit. Okay, right now we're just focusing on radioactive decay. And for radioactive decay, you always have three elements. You have what's called the parent nucleus on the left side, the daughter nucleus on the right side, okay, and whatever type of radiation it is, alpha, beta, gamma, whatever. Okay, the mass number has to be the same on both sides, and the atomic number has to be the same on both sides, just like we saw before. Okay, now, again, pause it here if you need to add this to your notes. Okay, and I said this before, and you should already have this in your notes, but again, pause it here just to make sure that you have this information, especially pertaining to the neutrino and antineutrino. Okay, this slide is basically just summarizing the main types of particles we talked about before and how you write them in nuclear notation: proton, neutron, electron, aka beta minus particle, a positron, aka beta plus particle, antineutrino, neutrino, alpha particle. Okay, so if you want to add this in your notes, you're welcome to, but you should already have this information somewhere in your notes. Okay, so I just want to show you a few more examples of radioactive decay equations, and then your next assignment is going to be working on a worksheet finishing out these equations. Okay, so here are four different types of radioactive decay equations. This first one, a lot of the time you would be given problems where you're given part of the equation and you have to fill in the missing piece. And you'll see in the next slide what I mean. But this first one is uranium-238 is undergoing radioactive decay. Specifically, this is an example of alpha decay. And I know it's alpha decay because guess what? There is an alpha particle right there. And turning into thorium-234. Now, if you don't know these atomic numbers, like I don't know the atomic number of thorium off the top of my head, that's where you would use a periodic table. And I will give you a periodic table for this next assignment. Okay, so this is an example of alpha decay. Here you have thorium-234 undergoing radioactive decay and turning into palladium-234. This is beta minus decay. I can see right away this is an electron, aka a beta minus particle, and this is the corresponding antineutrino that has to be included for completeness. And so this is example of beta minus decay. Okay, and then this is magnesium-23 undergoing, this is beta plus decay and turning into sodium-23, and this bottom one is gamma decay. Notice in gamma decay, nothing really changes. You have like radioactive thorium that emits a gamma particle, and it's still thorium. And so it's not very common to see gamma decay in IB problems just because nothing changes and it's maybe too easy of a problem. But there is an example of gamma decay. Okay, so you would be expected to easily identify what type of decay you're seeing and fill in some of the blanks given part of the equation. So pause it here if you want to write any of that down, and then we'll do one or two quick examples before I finish this video, and then you should be able to work on your next assignment over radioactive decay equations. Okay, so just really quickly to state each type of decay equation and fill in the missing pieces. Okay, so I'm looking at this. AM, I don't know what element that is, so I'm going to go to my periodic table and I look for AM on my periodic table. I want to say that's americium, but I could be wrong. It is, it's atomic number 95. Okay, and so that's going to be americium 241, atomic number 95. Right here, He, that's helium. I know that's got to be alpha decay, okay, just because there's an alpha particle there. And then I need to think, okay, 2 plus what number would give me 95? Well, that would be 93. Okay, now the reason I can do that is because I know that the mass number has to be the same on both sides of the equation, and the atomic number has to be the same on both sides of the equation. Okay, I did the same thing with the mass numbers. 4 plus what number would give me 241? And that would be 237. Now, that says 7 by the way. Let me erase that. Okay, so 237, 93, and I don't know what element has atomic number 93, so I go to my periodic table and I look right here. Atomic number 93 is neptunium, Np. Okay, so to finish off this problem, I would just write Np. Okay, so americium 241 undergoes alpha decay and turns into neptunium 237. Okay, so that is just a simple problem with a radioactive decay equation. Now, let me just do a couple more. Pause it here if you need to. The second one right here, I have carbon 14. I happen to remember carbon has an atomic number of 6. Otherwise, I would look at my periodic table. Nitrogen has an atomic number of 7. And this right here is a neutrino. However, you have to ask yourself, okay, 14 equals 14. A neutrino would be 0, 0, plus, well, if I have 14 on the left and 14 on the right, I need, whatever goes here, I need to have a mass number of 0. And then if you want to make the atomic numbers match on both sides, 6 equals 7 plus 0 plus what? Well, this has to be -1. Okay, so what is 0, -1? That is an electron. Okay, now if you're looking at this closely, you might be thinking to yourself, hopefully you're thinking to yourself, wait, this is beta minus decay. Okay, I know it's beta minus decay because there's an electron. Shouldn't that be an antineutrino instead of a neutrino? Yes. Okay, so there should be a line over this neutrino like this. So let me rewrite this equation just so you can see it better. Okay, this equation should look like this. I think there was a mistake with this question. I did not write it, I just copied it. But that should definitely be an antineutrino because it's beta minus decay. Okay. So that's just to give you an example of what some of these problems might look like with radioactive decay equations. Now, I don't want this video to be too long, so I'm going to stop it here. In the next video, I'll do a few more examples, but you should now at this point be able to work on your radioactive decay equation worksheet. Okay, it's a very simple worksheet. I'll make sure to attach the periodic table with it, and then I'll post the solution so that you can check your work. Please let me know if you have any questions. Um, I'll see you in the next video.